have same molecular formula, conformers have same molecular formula, okay, same molecular formula, but a different spatial arrangement, due to C single bond rotation. Now, very important thing, those who, if you have watched our stereochemistry video, we have also talked about configuration, that is your stereoisomers. We have talked about the stereoisomers, which are configuration. Okay. So over there we have seen that there are two molecules having the same molecular formula but different spatial arrangement due to chiral carbon. Chirality is very important concern for the stereoisomerisms. But for over here, the conformers do not have a chiral carbon, but they can produce a different spatial arrangement due to C single bond C rotation. Now, for example, I'll just like to give the example of ethane. CH3, okay, this ethane. So now these two carbon I will write in a Newman's projection formula, that if you watched our earlier video, you know what is Newman's on sawhorse. Of course, we have mentioned only part 1 in the YouTube. If you want to subscribe and also subscribe our Growwell Video Class, then you get part 2. So over there we mentioned that if we have this structure in conformer, now this carbon, one carbon I can see over here, okay, and the back side another carbon is also present. Now these are the 3 hydrogen I have represented. Now if you see, there is a dihedral angle or torsional angle. This is theta. Theta is nothing but torsional angle or dihedral angle. This angle is very important to understand the stability of conformers. Okay. Now the another, if theta is 60 degree over here. Now if I go for 0 degree conformers, then you can see the hydrogens are quite close to each other. Okay, here theta is 0 degree. Now over here we call them, this is a gauche configuration, gauche, okay, and this is eclipse for the ethane. Now of course, when ethane is this hydrogen is repelling each other, it is more unstable. That's not a stable conformer. This is a stable conformer because the theta is, the hydrogen is away. So van der Waals repulsion, that is a main concept over here. So van der Waals repulsion is more over here. So that's why energy associated with this compound is high, okay, and this is stable. So if these two compounds undergo a reaction, okay, this will react fast because this is already in a stress condition due to the van der Waals repulsion. Now coming to the next example, butane. So how butane produce conformers? So in butane we have the starting, the conformers is CH3, both the opposite side, okay. Now you have 1, 2, back side 3, 4, okay. So 4 butane structure. Now if you see the dihedral angle between the 2 methyl group, okay, it is 180 and there is no repulsion at all. So this particular conformation is known as anti-periplanar, which is more stable, okay, because of lack of van der Waals repulsion. Now if I move to 60 degree, if I rotate 60 degree rotation, okay, and the compound become like this. So you have the 60 degree methyl group will come over here, the back side methyl group, okay, the front side hydrogen, the top methyl group, and the hydrogen. So if you see, the methyl group is still 120 degree apart, okay, and this makes them less stable than this form. So what is this name? Anticlinal. Anticlinal. Okay. Now if I go for another 60 degree rotation, it will come over here. So the molecule can look like this. So this is CS3, this is CS3. Now you can see this structure, the angle between two CS3 is 60 degree, the dihedral or torsional angle, and this is known as synclinal or gauche. Okay, so definitely this is going more towards the CS3, so van der Waals repulsion is increasing. Okay, so stability is decreasing over here. Okay, now this is associated with around 3.8 kilojoule per mole energy, 3.8 kilojoule per mole. Okay, this structure, and over here, now one thing, this is more unstable because this is energy associated with the around 16 kilojoule. Yeah, it is 16 kilojoule per mole. And why so? So if you see the CS3 and H, quite, this is an eclipse form, okay, and that's why the energy is high. But over here the hydrogen is apart, and CS3 also not fully apart like 180, but it is 60 degree. So that's why it is 3.8. Now this will be the highest because over here the CS3, both the CS3 will be eclipsed form, and hydrogen also are eclipsed form. So this is your syn periplanar. This is known as syn periplanar, the structure, and the energy associated with is highest 18 kilojoule per mole. So this can be a good question of GPAT. Who is the conformer of butane is most least stable? That is, answer is syn periplanar. Okay. So now after that, let us move to cyclohexane. Cyclohexane, we have the different conformation of cyclohexane. As per the Beer-Stein theory, okay. So what happened? This is 120 degree, but sp3 it is 109.8 degree. You just find it out. I just this is an sp3 bond angle. So carbon want to adapt this bond angle, which is more stable tetrahedral form. So that's why the cyclohexane hexane can take up a chair form, okay, or a boat form. But the boat form, the hydrogens are quite close, which can again show the van der Waals repulsion, which is known as transannular strain or pre-log strain. Transannular. Okay. Now, if you know, this is a structure known as decalin. This is a structure of decalin, DECA. Now, decalin also produces a transannular strain due to the two hydrogen or pre-log strain. That's why these two structures are not stable. But cyclohexane, the chair form, which is also can be written, some sort of butterflies structure. This chair form is stable one. Now, only thing is the cyclohexane always try to